remaining 3 lectures left for us, right? But I think with the remaining content that we have, maybe if we go through very fast, maybe we can complete all the content within next week, and the last week will probably for revision or review the content before the examination. And as we talked before, I think we will set the examination date on the today on the 1st May, which is on Wednesday, and for the time is from 1 p.m. to 4 p.m. Here. The venue is here. So I will announce formally on the my field again for the examination date and time, but for now let's test on the 1st May. Okay. วันสอบตอนนี้กำหนดเป็นวันที่ 1 ตอนบ่ายหรือจะประกาศยังไงคะคือที่ไหน Okay. And for today we use lecture slide number 14, which we will continue the content of the equilibrium conversion, and mostly the content for the lecture today we will see some example for the heterogeneous system, and we will see the sample for the multi-reaction conversion or equilibrium as well. And for the next lecture, I think we can cover all the workshop or the example for the multi-reaction equilibrium that we have left. So mostly today I think we don't need to use the laptop, but next time please make sure to bring your laptop with you. Okay, so let's start with the recap the previous content that we have learned before. This is the relation or the expression that shows the relation between the Kutarski and the equilibrium constants. With the importance of this expression is if you know the temperature, then the equilibrium constant is fixed, and then you can calculate the equilibrium reaction coordinate or the composition of species at the equilibrium. So this equation is very important for determining the mole fraction or the composition of the species at the equilibrium or the maximum conversion. And from this fundamental equation here, we can divide it to consider on each special case, for example, for the reaction in the gas phase. So in the gas phase, we can change the Kutarski of species at the standard state to the standard state pressure, which is equal 1 bar. So in this case, as well, we can change the Kutarski of species in solution in form of the Kutarski coefficient in space, and also the mole fraction in gas phase and total pressure. So in that case, we can rearrange from the fundamental expression here into this one. So this expression is another important equation when you deal with the gas phase reaction, gas phase chemical reaction. So you will start with using this equation. So this one that I have to remind you again is here is the power of the total Stoichkov number, not the individual Stoichkov number for each species. This total, and this is the Kutarski of species in solution. So you can see that we have the cap both of the profile symbol here, which means the solution in the equilibrium mixture. And from this one, you can simplify it based on the special condition that you can apply to the system. For example, if you can consider your equilibrium mixture as the ideal solution, in that case you can change the viscosity coefficient of the equilibrium mixture into the viscosity coefficient of pure species. So in that case, the viscosity coefficient with the cap is changed to without the cap. This means the viscosity coefficient for the pure species. And you can find the viscosity coefficient of the pure species from the equation that I showed you before, from the parameter from the Lee-Kessler parameter, which is normally included in the appendix in the end of the textbook, or sometimes you can use the second variable equation to determine the viscosity coefficient of the pure species. And actually for the application of this equation, we have already see some example in the previous lecture. You can go back to see the exercise in the lecture number 13 for this one. And one thing is for sure is usually the real solution is normally not ideal solution. It's very rare to assume the solution in the practice to be ideal solution. So for the assumption of the ideal solution, we just use change the viscosity coefficient of the mixture into the viscosity coefficient of the pure species just for finding the initial gas before you continue to calculate for the viscosity coefficient of the solution. But anyway, if from this equation and the reaction that you consider is carried out at the very low temperature, very low pressure and high temperature enough. I mean, the high temperature that means is above the room temperature is okay. But the low pressure, in that case, you can assume the ideal gas state or the gas species in the system that has that react the chemical reaction. We have like the ideal gas. In that case, you can change the viscosity coefficient of the mixture into the viscosity coefficient for the ideal gas, which is equal to 1. So in that case, if your reaction that you consider is carried out at a low pressure and high temperature, in that case you might be able to assume that the ideal gas state is justified. So in that case, the viscosity coefficient here can be equal 1. And this can simplify the equation here. If the purple parameter here is equal 1, then the equation that you can use is simplified to these equations. So this equation is useful when you can assume for an ideal gas state and every species in your chemical reaction is intact. So then you can use this one. And you can see that actually the unknown parameter included in this equation is just the reaction coordinate, which is embedded in the mole fraction here, and pressure here, and the temperature, which is also embedded in the equilibrium constant. So actually there are only 3 parameters here. So if you fix only 2 parameters, then you can find another parameter separately. So for example, if you know temperature, then you can calculate for the equilibrium constant. You also know pressure. Then from this equation, you can find the equilibrium reaction coordinate here, which is the mole fraction is function of the reaction coordinate, or the vice versa for the other parameters. Okay. So in the previous lecture, we see the example when you deal with the gas-phase reaction already, and we use this equation and also this equation for the calculation. And what happens if you have the reactions that each species in the reaction is not in the same phase, or if it's not in the gas phase. So in that case, for example here, if you have both gas phase species A and the liquid phase from species B, and react together, and you get the C species in the aqueous phase. So in this case, you have both gas phase, liquid phase, and actually another one is the aqueous phase. So when you have more than one phase that you have to deal in the chemical reaction, usually actually you can start with the same from the fundamental relation between the equilibrium constant and the ratio of viscosity here. This is the equation of the chemical reaction equilibrium. But then you have more than one phases in the reaction. You have another criterion of a phase equilibrium that you can use for the calculation. We will see the example later. So the criterion that you have learned from the phase equilibrium is the viscosity of any species should be equal in every phases. So in this case, you have vapor liquid, right? So viscosity of species I in liquid phase should be equal to the viscosity of species I in the vapor phase. So this one can use with the equilibrium equation of the chemical reaction equilibrium here to calculate for the reaction coordinate again. And this is just rearranged or simplification in the case of that we change from the fundamental equation here in the gas phase reaction. You can change into this form, or if it's in the liquid phase reaction, you can change this equation of the chemical reaction here to this form. So the difference between these two equations is how you change the viscosity of the species in solution, the viscosity that has the cap here. For the gas phase here, you change in the form of the viscosity coefficients and mole fraction in gas phase. But in the case of the liquid phase, you change the viscosity into the activity coefficient for the gamma symbol and the mole fraction in the liquid phase, which is the xi. And also continue with the viscosity here, which can change into the form of volume and pressure that I have shown you in the previous reaction. But anyway, let's see the sample if you have the heterogeneous reaction. So in this example, they said that please estimate the composition of the liquid and vapor phase when the ethylene reacts with the water to form ethanol at 200 degrees Celsius and 34.5 bar. So actually this reaction is the same reaction that you have learned in the previous lecture, but that one, if you remember, it is the vapor phase hydration of ethylene. But this one is the liquid and vapor phase. So this time we have more than one phase that we have to deal in the reaction. So yeah, they assume that no other reaction, just one reaction here. And make sure that they have both liquid and vapor phases when the reaction occurs at 200 degrees Celsius, 34.5 bar. So usually when you have a heterogeneous system reaction, you have more than one phase in the system. The method that you can do is you can consider all of the species in that system in just one phase. For example, you can start by considering the system of reaction in the gas phase for every species, or you can start by thinking that every species reacts in the liquid phase as well. And then you can use the criteria of the phase equilibrium to simplify the calculation. So in this case, it just be more convenient to chemical reaction for every species occur in the gas phase at first. So let's think that the ethylene reacts with the water in the gas phase, and then we get the ethanol in the gas phase as well. So if so, from the fundamental equation here, you can write these equations certainly. So this is the equation of the chemical reaction equilibrium, and for the right hand side term is still the equilibrium constant here. For the left hand side, you just change the viscosity coefficient, viscosity at the standard state, the denominator here, the viscosity with the degree superscript here. You can change into the standard state ratio here. And with the summation of the, so totally it means that the numerator in this fraction here is the viscosity of the ethanol, which is product here, over the standard pressure. And for the numerator here, you have the viscosity of the ethylene over the standard pressure times with the fraction of the viscosity of water over the standard pressure as well. So in summation, when you eliminate the same term together, then you get only one standard pressure here. You can follow this one. This side, are you okay? So you just change this one into the this one. So you change it to this for every species, and then the standard state pressure here will be eliminated together, and then the left one that you have is the one standard pressure here. Can you get it? So viscosity from the ethanol, right? If I know this one is this one, and this shift back to the situation here, this one. So if finally, if you eliminate every parameter, then you get this equation. So this one will carry out the reaction at the 250 Celsius. So with the fixed temperature, you can calculate the equilibrium constant. Right? So the procedure to determine the equilibrium constant is the same that you have learned in the previous lecture and the previous exercise that you have done before. So in this case, you can determine the equilibrium constant at 200 degrees Celsius, which is equal to the 0.031. Yeah. Then now actually for this equation you have already determined the equilibrium constant. The next thing that you have to do is you have to clarify the viscosity of each species here, which is equal what term in the mole fraction. So to do that, you can use the criteria of equilibrium, phase equilibrium, to change the viscosity of the gas into vapor or vapor into of the gas into liquid or viscosity of the liquid to vapor, because the viscosity of the species in the liquid and vapor phase should be equal together. So in this case, you know that the reaction occur in both liquid and gas phase. So the water will be in the liquid phase. The ethanol will be in the liquid phase. But normally in the practice, the ethylene is very difficult to condense into the liquid phase. So in this case, only the ethylene that exists in the gas phase here. So we change the viscosity of the ethanol from vapor. The superscript B here means the vapor phase, and the L superscript L here is the liquid phase. So I change the viscosity of the ethanol in the vapor phase into the liquid phase. As well with the viscosity of the water in the vapors to the liquid phase. Then you can change the viscosity in terms of the mole fraction and the acting coefficient for the liquid phase, and the mole fraction and the viscosity coefficient for the liquid phase. So normally you just put the right hand side equation back into the equation here. So you get the equation as shown here. So as the numerator here, as you can see, is in the liquid phase. So the form here is the mole fraction of ethanol in the liquid phase times with the activity coefficient again, and the viscosity of the ethanol in the liquid phase, the pure ethanol in the liquid phase. Same as the numerator here, this is for the gas phase of ethylene, and this is for the liquid phase for the water. Then, usually for the pure species, now we have the viscosity of the pure species for the ethanol and water here. How we can change this viscosity into the parameter that we can measure, for example, pressure. So usually for a pure species, the processing liquid and vapor phase are easily equilibrium. And you know that the viscosity of the vapor in the vapor phase should be equal to the viscosity in the liquid phase. And actually is equal to the viscosity of pure species at the saturated condition. Be careful that here has the cap here, which means in solution. This is also mean in solution or in mixture. This one is the viscosity of pure species at the saturated condition here. So the sat here, sat superscript here refer to the saturated condition. So from the definition of the viscosity coefficient, and you consider as the saturated condition. So the viscosity coefficient is equal to the viscosity of pure species divided by the pressure at the saturated condition. Actually, the P sat here is equal to the vapor pressure. So you rearrange this equation to get the viscosity of pure species at saturated condition. Then you get the viscosity coefficient times with the pressure at saturated. And from this one and this one is equal to the viscosity viscosity of the water and the ethanol here. So then you can substitute the viscosity coefficient times with the vapor pressure back into the equation. So again, the symbol phi with superscript set here is the viscosity coefficient of pure saturated liquid and vapor at the temperature of the reaction temperature and the saturated pressure or vapor pressure. This is the definition of the viscosity coefficient at the set T. And the T set is the vapor pressure that we have known before, the same. This one is the viscosity coefficient that is determined at the vapor pressure. Okay, so then when we have this equation already, you can change the mole fraction of each species into the function of the reaction coordinate to reduce the unknown parameter, and then you can solve the equation. So the next step is you change the mole fraction in form of the reaction coordinate. So you know that the summation of the mole fraction for every species should be equal 1. So in this case, in the vapor pressure, you have every species in the vapor pressure. So in the case of mole fraction of ethylene should be equal to the 1 minus the mole fraction of the remaining species. In this case, is the mole fraction of the ethanol and water. And just leave this relation a little bit here, and then you can consider from the criterion on the phase equilibrium again. You know that the viscosity coefficient of PCI in solution in the liquid phase and vapor phase should be equal. Then you change the viscosity into the activity coefficient or the viscosity coefficient here. Then from the previous slide, you know that the viscosity of pure PCI in the liquid phase equal to the viscosity coefficient that is determined at the vapor pressure times with the vapor pressure itself. So I change the purple parameter into the two parameters here. Then, if for the initial calculation that you can use for determining the initial gas for the next time for iteration, or sometimes you can determine just for the basis that you can see what will happen that you assume the ideal gas solution. In that case, if you assume the ideal solution, in that case you can change the orange term, which is the viscosity coefficient of the solution, into the viscosity coefficient of pure species. So then the orange term is changed to the pure species, the property of pure species. And then you rearrange again to get the expression in terms for the mole fraction of each species. Then you substitute back for replace the mole fraction of ethanol and water in this equation. So you can see that this one is just the same, but I use the subscript of each species to identify that which term is for which species. So this term is the same with this one, but this for the ethanol and this for the water species. So from this equation, the unknown parameter that we cannot determine here is the mole fraction in the liquid phase, which is written in the x subscript with the I for the ethanol or the water here. So that means that we have to estimate the mole fraction in the liquid phase first. So in the case that, as I just told you, that usually in the real situation, the ethylene is very difficult difficult to condense and it is more volatile compared to the water and ethanol here. So we can assume that the mole fraction of ethylene in the liquid phase is equal to 0. It means that no ethylene in the liquid phase. If so, we can write the mole fraction of water equal to 1 minus mole fraction of ethanol. Because in the liquid phase, this in the liquid phase, this in the vapor phase. This vapor phase, this liquid phase. So liquid phase we don't have the ethylene. So you have only water and ethanol. So the mole fraction of water is equal to 1 minus mole fraction of ethanol. Then actually you have all of the equation that you needed for solving this equation already. But how to do that is first step is you have to assume the mole fraction of ethanol first to calculate the mole fraction of water. So the first step is you assume the initial gas value for the mole fraction of ethanol first. Then from this equation, it means that you can calculate the mole fraction of water. Just 1 minus. Then the next step is if you know the mole fraction of water, then mole fraction of water and ethanol, then you can calculate the activity coefficient from the model that you have known. The activity coefficient is usually in the function of the mole fraction in liquid phase. So far that you have used the model of the MRTL, you have the Wilson equation, you have unit fact that you have that were done in the exercise. So in that case, you just choose the model that you want to use for determining the activity coefficient, then you can. So the next step, first you assume the initial gas value of the mole fraction of ethanol. Then you can calculate the mole fraction of water. And with the both mole fraction of ethanol and water, you can calculate the activity coefficient of water and ethanol. Then you can substitute all of the powder back into the equation of mole fraction of ethylene here. So you know the total mole fraction of ethanol here is the initial gas value. The activity coefficient of ethanol here is determined from the initial gas value here. And again, the mole fraction of the water is from the expression. The activity coefficient is for the second step. So as you can see in this equation, the thing that you have known is pressure you know, which is 34.5 bar is long, and the Psat or the vapor pressure you can calculate using the Antoine equations. So it means that from this equation it seems that only parameter that you have to determine before calculate this calculation is the Fogarty coefficient at the vapor pressure of this species for the ethanol and the water. And just this is here for a while. And actually another equation that you can use for determining the mole fraction of the ethylene here is another equation from the chemical reaction equilibrium that we have read before. So you know that the K equilibrium constant is equal to some very large term here and come with the standard pressure here. So this initial gas, this is determined. This can be determined. P is, you know, the mole fraction is from this one, and the mole fraction is calculated from this particular thing here. So I will talk for the procedure to calculate the Fogarty coefficient again. So just for this step, it seems that you can calculate the actual mole fraction of ethanol by using this equation only. Just use the iterative procedure to change the guessing value of the mole fraction of ethanol until this equation is satisfied. The K equilibrium constant you know already from the pressure, from the temperature that is fixed for this reaction. So just use the iterative procedure to recalculate until the guessing value of the mole fraction of ethanol make this equation is satisfied. This one is also come from the assumption of the ideal solution as well. So from the equation that we have read in the previous slides, in that case it's still in the term of the Fukasi coefficient of solution, but we use the assumption of ideal solution to change the Fukasi coefficient in solution to the pure Fukasi coefficient of the pure ethylene. And that is all the procedure for determining the mole fraction of ethanol. So maybe you can use these two equations, or in my preference I try to do every each step and I substitute this mole fraction of ethylene into this equation and use the solver to make this equation satisfy by changing the guessing value of the mole fraction of ethanol. It can be in that way as well. This, as I said, the vapor pressure of the ethanol and water you can calculate from the Cantor equation. And for the Fukasi coefficient of the pure species that I have here, that's one, as I said before, you can use the parameter of Lee Kessler that usually provide in the end of the thermodynamic textbook to calculate the Fukasi coefficient. On the other way, you can use the second value equation that I have shown here, this one, to calculate the Fukasi coefficient of each species as well. This one is the Fukasi coefficient of pure species, this one. In this equation, you have to know the reduced pressure and reduced temperature. The subscript R letter here means reduced. So you can calculate by dividing the pressure by the critical pressure, or in the case of the reduced temperature, you can divide the reaction temperature by the critical temperature. And usually the critical temperature, critical pressure, and omega here is eccentric factor, which is the parameter show how the molecule is in circular, how much is in circular form or in circular shape. So in this case, these three parameters are the property of the component. So different components have the different critical temperature, critical pressure, and eccentric factor. And with these three factors, you can find anywhere online or even in the lab, in the appendix of the textbook as well. So in this case, you find the data from the appendix, and then you can calculate the reduced temperature, reduced pressure from both equations here. Then you can calculate the reduced vapor pressure too. How to calculate this? Actually, it's the same with this equation, but you just use the vapor pressure as the numerator and divided by the critical pressure. Then you get the reduced vapor pressure. So just change the pressure of the system to the vapor pressure of that species. Then you can calculate the radial pressure here. The critical temperature is fixed for certain components. Right? And B0 and B1 here. Again, the number 0 and 1 here is not the power. It's not the power of parameter. It's just the symbol that show the difference of parameters. That is so. B0 you can calculate from this equation, which need to use the radial temperature, which you have already calculated. And B1 you have to use the radial temperature as well, then you can calculate the B1 for each species. Then you have B1, B0, omega, TR, then you can calculate the Fugazi coefficient for each species. And this one, how to calculate this one? The difference here is the superscript with the set here, mean the saturated. The difference here is you use the radial pressure at the vapor pressure. So you calculate the same way with same equation, but in this case, you have to use the radial vapor pressure instead of the normal radial pressure. Then you can get this one. The equilibrium constant you can calculate from the temperature that you have known with the procedure that you have ever done before. It is the same that we have done before in the previous example, in the previous workshop that we have go through. The vapor pressure of water and ethanol, you can use the Antoine equation to determine both of these. So in the final, you get the Fugazi coefficient for the pure species at the reaction condition. And another one is Fugazi coefficient of the pure species at the vapor pressure here. And let me go back a little bit. So you can see that now you can you know every parameter based on the initial gas value of a mole fraction of ethanol oil. So by iterative procedure, then you can change the mole fraction of the ethanol here until the right hand side term here is equal to the equilibrium constant value that we have determined before. So the standard state pressure here is equal. Do you know the number of this one? Standard state pressure is equal to 1. What is the unit? 1 bar. Yeah, 1 bar. So please make sure that every unit of every parameter in the picture here in the same unit with 1 bar, or you have to reunit for every parameter in the same unit in this equation. This one?
Yes, this for the second format, you are having a mole fraction. Why is it that the mole fraction of the liquid phase was not considered?
Why the mole fraction of ethylene is not considered in the liquid phase?
Yes.
That's the question. Because it's from the property of ethylene itself, and actually it's also the assumption that we can say, because in the practice on the real situation, the ethylene usually in the gas phase form, even at the high pressure, it's very difficult to volatile. So then we can assume, actually, as you know in the phase equilibrium, every species has to be exist in every phase, right? But in this case, just assume that the mole fraction of ethylene is not exist in the liquid phase because it is difficult to condense into liquid in this case.
Or in examination situation, how can we know one that is more volatile or we consider volatile?
Do you mean that how we can assume like this for the other cases?
In case of examination now, how can we know the components that is more volatile than the other? Should we consider the molar mass?
The what?
The
Should we
molecular mass.
the molecular mass for
For each of the constituent organic compound.
the molecular mass for why do you want to use the molecular mass to
Determine the volatility of the component.
determine what?
How volatile it is volatile.
How volatile it is?
Yes.
It can, if you can determine. Yeah, but you can check with the vapor pressure or the vapor pressure of the component at the pressure of the system. So, for example, in this case, we do the reaction at the 34.5 bar. But in this case, you can check the vapor pressure of this component of the ethylene at the 200 degrees Celsius 35 bar, which is the ethylene is still the gas phase in this condition. Yeah, you can check with the condition of the reaction for the each species that which species should be in the gas phase or in the liquid phase. Yeah, and I just think of something and I just forgot it already. So yeah, if I can remember it again, I will say. Okay, so yeah, you can check based on the condition of the reaction. For example, the temperature and pressure, and check with the vapor pressure of each component that if that component should be in the gas phase or the liquid phase in that condition. Okay. So if you calculate correctly based on the assumption, if you remember this example here, we make the equation, this one, based on the assumption of the ideal solution, both in the vapor phase and liquid phase. So in this case, if you still use the assumption of ideal solution, you will get the mole fraction like this. So you can try to do the calculation. And yeah. So if you remember the procedure here, you make the satisfaction of the equation by changing the mole fraction of the ethanol, right? Then you can calculate the mole fraction of water. And when you know the mole fraction in liquid phase already, you can calculate the mole fraction of each species in the vapor phase using this equation. So the Y or mole fraction in the vapor phase here is determined from this equation. And both the mole fraction in liquid and vapor phase should be equal one for every species, sum together. Okay. Do you have any questions? Do you have this one?
Formula we are going to use to get the mole fraction for the steam and ethanol.
Sorry? How?
If it is formula we are going
personal. Yes. So you can try 0 to 1. Yeah, for the move action, right? So usually I just put 0.5, and yeah, if you can get very close to the actual answer, the number of the iterative will be reduced. But in the end, the iterative should be go to the actual uh, answer as line. So the initial guess of no fraction will be between 0 and 1, like no fraction, 0 and 1. So you can type 0.5. But in this case, you can see that the actual answer is 0.06. So if you start with 0.5, it might just need many turns of iteration to get to the 0.06. Right.